As I just said, it is very nice to claim that we can approximate our function with an nth degree Taylor polynomial, but of course the statement is quite meaningless if we are not able to say something about the difference. So that's what we are going to look at. So we look at the difference between f of x and the value of the Taylor polynomial, nth degree Taylor polynomial with base point a. Now, let us recall the definition of the nth order Taylor polynomial at base point a, evaluated at the point x. So we have f of a plus the first derivative of f at the point a multiplied by the difference of our point x and the base point, plus the second order derivative evaluated at the point a multiplied by the difference between x and the base point a divided by 2 factorial, and so on. So we have this nice expression, and here I almost forget to include the nth derivative of our function f evaluated at the point a. So we have this function, we have the point a, and this is what we have. Okay, now what is the statement? Taylor's theorem tells us precisely, gives us precisely a bound on the difference between the Taylor polynomial and the function value. It is theorem 12 from the corresponding paragraph, and it is called Taylor's theorem. So we suppose that now f is defined on this interval I, which is the interval a plus delta a, or a minus delta up to a plus delta. So we have this interval I sitting here. We suppose that this function f is now not only n times differentiable, but n plus 1 times differentiable. Otherwise we cannot say anything about the difference between the nth degree of the nth order polynomial, Taylor polynomial, and the function. So what is the claim? There exists a point S in between x and a, so it depends on x and a. It's a point S between a and x. We don't know what point, but it is somewhere where between a and x. So let us draw point x over here, and then this point S is somewhere in between. Okay, so there is a point where the following holds, that the difference between the function evaluated at the point x and the nth order Taylor polynomial with base point a evaluated at the point x is precisely, this difference is precisely the n plus 1th derivative evaluated not at a but at this unknown point S. Maybe it's better to put it in green. And the rest of the expressions are similar as before. We divide by n plus 1 factorial, and we multiply with the difference of our point of interest x and the base point a to the power n plus 1. Now clearly we know a precise expression for the difference between our function value and the nth order Taylor polynomial at the point x. But since we do not know S, we cannot compute this precisely, and what we only can do is bound this difference. So the consequence of our theorem is the following, that the difference between the function value and the value of the nth order polynomial evaluated at point x and the polynomial associated with base point a. So we call this difference the error that we make by computing the value of the nth order Taylor polynomial instead of the value of the function itself. Then this difference cannot be larger than if we take the maximum of the nth plus 1th derivative over the interval a up to x. So the function value of the n plus 1th derivative evaluated at the point s between a and x can never be bigger than the maximum value that can be attained if we vary all the input values between a and x. So we get max over all points y in the interval from a up to x of the n plus 1th order derivative evaluated at the point y. And that is the only thing that we cannot precisely compute, that we cannot control precisely, but the other terms are known. So we have to divide by n plus 1 factorial and multiply by the difference between x and base point a to the power n plus 1. So this maximization is the thing that makes this bound a little bit harder to assess. Now let us apply this theorem to one of our previous examples. So what we did a few videos ago was to compute the 4th order Taylor polynomial for with base point 0 associated with sine of x, and we have seen that this is equal to x minus x squared, x to the power 3 over 6, and we did evaluate the value at point 1, which is equal to 1 minus 1 over 6. And it is approximately equal to 0.833 and something. And the question is, what is the difference between the sine of 1 and this the value of the 4th order polynomial at 1? Well, according to our theorem, this is less or equal to the maximum value of the n plus 1th derivative, which is the 5th derivative of sine of x, and the 5th derivative is cosine of x, in this case cosine of y, and we take now y between our base point 0 and our point of interest 1, and of course we have to take absolute values because we have to bound a difference in absolute value. We have to divide by n is 4 plus 1 factorial is 5 factorial, and we have to multiply it by 1 minus 0 to the power 5, which is 1. Now, of course, if we are close to 0, then cosine of 0 is almost equal to 1, so this maximization gives us 1, so this is equal to 1 over 5 factorial, and 5 factorial is 120. So this difference between sine of 1 and the number 5 over 6, 0.833, is smaller than 1 over 120. So this is approximately equal to 0. Well, at least smaller than this. Okay, now in the next video I will calculate another approximation and give a bound so that you can see how to compute these things.